Yes, a standard breaker can provide protection for a generator when national electrical code requirements are met, taking into account the generator's output capacity and breaker characteristics. Common breakers have ampacity ratings higher than the rated output of a typical generator. However, the breaker's trip curve must be considered. Standard breakers have an instantaneous trip for short circuits and a thermal magnetic trip for overloads. Thermal breakers only have a thermal magnetic trip. Thermal magnetic trip curves have an inverse time current characteristic. At high currents, they trip faster, while at low currents, they take longer to trip or even allow current to flow continuously if below the magnetic trip threshold. Generators have a maximum output capacity. If the load exceeds the generator's capacity, it can cause an overload. Standard breakers can protect against overloads by tripping when the current exceeds the generator's rating for a prolonged period. Thermal breakers are particularly effective for this purpose. If there is a dead short fault in the generator circuit, the fault current will be limited by the generator's internal impedance. A standard breaker can trip instantaneously if the fault current exceeds the breaker's instantaneous trip rating. In the event of an arcing fault, the fault current may not be high enough to trip the breaker instantaneously. However, arc fault circuit interrupters, or AFCIs, can detect the unique signature of an arc fault and trip the circuit accordingly. Standard breakers, when selected and installed according to national electrical code requirements, can provide adequate protection for generators in most scenarios. They can protect against overloads, short circuits, and with AFCIs arcing faults. However, it is important to consider the generator's output capacity and the breaker's trip curve to ensure proper protection. Now let's delve deeper into the specifics of how standard breakers function in conjunction with generators, focusing on the critical aspects of overcurrent protection. Overcurrent protection is essential to safeguard both the generator and the connected electrical system from damage that can arise from excessive current flow. This can occur due to various reasons, including overloads, short circuits, and ground faults. Standard circuit breakers are designed to interrupt the flow of current when it exceeds a predetermined level for a specified duration. These breakers are typically thermal magnetic, meaning they employ two distinct mechanisms for tripping. Firstly, there is the thermal element, which responds to sustained overloads. Secondly, there is the magnetic element, which reacts almost instantaneously to high magnitude short circuits. The thermal element operates on the principle of heat generation due to the current flowing through a bimetallic strip. When the current exceeds the breaker's rated ampacity, the bimetallic strip heats up and bends. If the bending is sufficient, it triggers the tripping mechanism, opening the circuit and stopping the current flow. The time it takes for the thermal element to trip depends on the magnitude of the overcurrent. Small overcurrents may take several minutes to trip the breaker, while larger overcurrents will cause a faster trip. The magnetic element, on the other hand, is designed to trip very quickly in response to high magnitude fault currents. It consists of a coil that creates a magnetic field when current flows through it. If the current exceeds a certain threshold, the magnetic field becomes strong enough to attract a lever or plunger, which then trips the breaker. The magnetic trip is typically instantaneous, meaning it occurs within a few milliseconds. The National Electrical Code, or NEC, provides specific guidelines for overcurrent protection of generators. These guidelines are intended to ensure that generators are adequately protected from overcurrent conditions. NEC Section 445.12 specifies the overcurrent protection requirements for generators. It states that generators must be protected from overcurrent in accordance with their ampacity rating. The overcurrent protection device, typically a circuit breaker or fuse, must be sized no larger than the generator's ampacity rating. Furthermore, the NEC requires that the overcurrent protection device be readily accessible and located as close as practicable to the generator. This is to minimize the length of unprotected conductors between the generator and the overcurrent protection device. Now, let us consider the generator's output capacity in relation to the breaker's characteristics. Generators have a maximum output capacity, which is the maximum amount of power they can deliver without being damaged. This capacity is typically expressed in kilowatts or kilowatts. The generator's output capacity must be considered when selecting the appropriate size of the overcurrent protection device. If the overcurrent protection device is too large, it may not trip quickly enough to protect the generator from overload or fault conditions. Conversely, if the overcurrent protection device is too small, it may trip unnecessarily, causing nuisance tripping. The breaker's trip curve is a graphical representation of the time it takes for the breaker to trip at different current levels. Trip curves are typically provided by the breaker manufacturer. They show the relationship between the current flowing through the breaker and the time it takes for the breaker to trip. Trip curves are useful for selecting the appropriate breaker for a particular application. They allow engineers to determine whether the breaker will trip quickly enough to protect the equipment being served from overcurrent conditions. Additionally, the type of load connected to the generator can also influence the selection of the overcurrent protection device. Some loads, such as motors, have high inrush currents when they are first started. These inrush currents can be several times higher than the normal operating current of the motor. If the overcurrent protection device is not properly sized, it may trip due to the inrush current, even though there is no actual overload or fault condition. In such cases, it may be necessary to use a breaker with a higher instantaneous trip setting or a time delay fuse. Now let's move on to a more in-depth discussion of fault protection for generators. Fault protection is designed to protect the generator from damage caused by short circuits and ground faults. Short circuits occur when there is an unintended connection between two or more conductors. Ground faults occur when there is an unintended connection between a conductor and ground. Fault currents can be very high, and they can cause significant damage to equipment if they are not quickly interrupted. Standard breakers are designed to trip very quickly in response to high-magnitude fault currents. A magnetic element of the breaker is responsible for tripping the breaker in these situations. The instantaneous trip setting of the breaker determines the level of fault current required to trip the breaker instantaneously. The instantaneous trip setting is typically expressed as a multiple of the breaker's rated ampacity. For example, a breaker with a rated ampacity of 20 amps and an instantaneous trip setting of 10 times the rated ampacity will trip instantaneously when the current exceeds 200 amps. The generator's internal impedance plays a crucial role in limiting the magnitude of fault currents. Internal impedance is the opposition to the flow of current within the generator itself. It is primarily determined by the resistance and reactance of the generator windings. The higher the generator's internal impedance, the lower the fault current will be. In the event of a bolted fault, which is a direct short circuit, the fault current will be limited only by the generator's internal impedance and the impedance of the conductors connecting the generator to the fault location. A standard breaker can trip instantaneously if the fault current exceeds the breaker's instantaneous trip rating. However, it is important to note that the fault current may not always be high enough to trip the breaker instantaneously, especially in the case of arcing faults. Arcing faults are faults that involve an electrical arc. Electrical arcs are characterized by high temperatures and intense light. They can cause significant damage to equipment and can also pose a fire hazard. Arcing faults can occur due to various reasons, including insulation breakdown, loose connections, and corrosion. The fault current in an arcing fault may not be as high as in a bolted fault. This is because the arc itself introduces impedance into the circuit, which limits the current flow. As a result, a standard breaker may not trip instantaneously in response to an arcing fault. This is where arc fault circuit interrupters, or AFCIs, come into play. AFCIs are designed to detect the unique signature of an arc fault and trip the circuit accordingly. AFCIs work by monitoring the current and voltage waveforms in the circuit. They look for specific patterns that are characteristic of arc faults. These patterns include rapid changes in current and voltage, as well as the presence of high-frequency noise. When an AFCI detects an arc fault, it trips the circuit within a fraction of a second. AFCIs are required by the National Electrical Code in many locations, particularly in residential circuits. They are an effective way to protect against arcing faults, which can be a significant cause of electrical fires. In summary, standard breakers, when selected and installed according to National Electrical Code requirements, can provide adequate protection for generators in most scenarios. They can protect against overloads, short circuits, and with AFCIs, arcing faults. However, it is important to consider the generator's output capacity, the breaker's trip curve, and the type of load being served to ensure proper protection. In addition to the points already discussed, it is important to consider the coordination of overcurrent protection devices. Coordination refers to the selective tripping of overcurrent protection devices. The goal of coordination is to ensure that only the overcurrent protection device closest to the fault trips, while other overcurrent protection devices upstream remain closed. This minimizes the extent of the outage and allows the rest of the electrical system to continue operating normally. Coordination is typically achieved by selecting overcurrent protection devices with different time current characteristics. For example, a breaker close to the load may have a faster trip time than a breaker further upstream. This ensures that the downstream breaker will trip first in the event of a fault. Coordination studies are often performed by electrical engineers to ensure that the overcurrent protection devices in a system are properly coordinated. These studies involve analyzing the time current characteristics of the various overcurrent protection devices and determining whether they will trip selectively under different fault conditions. Another important consideration is the maintenance and testing of overcurrent protection devices. Overcurrent protection devices should be regularly inspected and tested to ensure that they are functioning properly. Breakers should be visually inspected for any signs of damage or corrosion. They should also be tested to verify that they trip within the specified time current characteristics. Fuses should be inspected to ensure that they are of the correct size and type. They should also be tested to verify that they blow at their rated current. Regular maintenance and testing of overcurrent protection devices can help to ensure that they will operate reliably when needed. In addition to standard breakers and AFCIs, there are other types of overcurrent protection devices that can be used to protect generators. These include fuses, molded case circuit breakers, and insulated case circuit breakers. Fuses are one-time overcurrent protection devices. They consist of a strip of metal that melts when the current exceeds a certain level. Fuses are simple and inexpensive, but they must be replaced after they blow. Molded case circuit breakers are resettable overcurrent protection devices. They are similar to standard breakers, but they are typically larger and have higher interrupting ratings. Insulated case circuit breakers are also resettable overcurrent protection devices. They are typically used in high current applications. The selection of the appropriate type of overcurrent protection device depends on the specific application and the level of protection required. In conclusion, standard breakers can provide adequate protection for generators when selected and installed according to National Electrical Code requirements. However, it is important to consider the generator's output capacity, the breaker's trip curve, the type of load being served, and the coordination of overcurrent protection devices to ensure proper protection. Regular maintenance and testing of overcurrent protection devices are also essential to ensure that they will operate reliably when needed. The selection of the appropriate type of overcurrent protection device depends on the specific application and the level of protection required.